Now, is there anyone else who was away yesterday and missed the test? Everyone else was here? Good. All right. We are on page 5. And I would like you to figure out of all of these ones, number 1, which one is the odd one out? Which one doesn't belong with the others? So I'm going to give you a minute, chat with your partner about it, okay? Once you have decided, check your answer with your partner. We have copper, gold, salt, and sulfur. You could, but there's one that's more obviously different. You're in my pocket, that's why. Where is it? There we go. All right. All right. Well, we're going to start by writing some symbols for each of these. Could you guys give me, and you can feel free to use your periodic table, which you should still keep with you. So if you've got your pink periodic table, please bring it out. If you have lost your pink periodic table, please let me know and I will get you a new periodic table. That's okay. Can you share off someone for today? Okay, cool. What is the symbol for copper? CU. What is the symbol for gold? AU. What is the symbol for sulfur? S. And do you guys know the actual chemical name for table salt? It is sodium chloride. And the symbols for sodium chloride are NaCl. NaCl, yes. And do you remember how you tell, how you write the symbol for an element in terms of capital letters and lowercase letters? First one is capital, any second letter will be lowercase. So if we look at NaCl, we have 2 capital letters. So we have 2 capital letters. And if I have 1 capital letter, how many elements do I have? 1 element. I have 1 element. I have sulfur is just 1 element. I have gold. How many elements? 1 element. But for sodium chloride, we have 2 capital letters, so that means we have 2 elements. But because we've written them together, right, one right after the other, they are stuck together, okay? Yep. They are stuck together. And if you have 2 elements stuck together, like Zeev said, that is a compound. COM, Pound. All right. Do the same little thing with number 2, okay? Take a look at number 2 and decide if you can pick which one. Oh, and I guess we should circle the one that was the odd one out. That was salt, because all the other 3 were elements, and that one was a compound. Try for the second one. Try it yourself and then check with your partner. So for number 2, you're looking at rust, silver, water, and wood. Rust is iron oxide. You just like messing with things. It's true. There are other ways of doing it, but so as Connor was pointing out, there are more than one way to classify these as having the odd one out, because rust is a solid, silver is a solid, wood is a solid, and water is a liquid. But for the purposes of this, because it is called Elements, Compounds, and Mixtures, that's the title of this, we're going to be looking and saying which is the odd one out in terms of that. So I just said that rust is made of iron oxide. So rust is iron oxide. If it's oxide, what element is involved? Oxygen. And the symbol for this will be Fe with a little 2 and an O with a little 3. So what that's going to look like is it's going to look like an Fe atom stuck to an O atom. Actually, not an atom. These are ions, but we'll get to that part later. So just pretend I didn't say that. 1, 2, 1, 2, 3. There we go. That's not an awesome representation of what that looks like, but it'll be close enough. You have a little clump that involves 2 iron atoms. Yes, so Fe2, that's our little 2. And then we have the O. We have 3 of them. So that's where those little numbers come in. Don't worry too much about the little numbers just yet. You're just getting a flavor of them. We'll be doing more of those in the next unit. Yes? Yes, although it's not called rusting usually, it's just called corrosion. Rust is specifically iron oxide, okay? But the process of corrosion where they react, or oxidation, is where a metal reacts with oxygen to produce the metal oxide. Yeah. Okay, so we have iron oxide. Silver, what is the symbol for silver? Ag. Okay, you can look that one up if you want to. What is the formula for water? H2O. Do you guys remember what that looked like? It's 1 oxygen with 2 hydrogens sticking off of it, very much like Mickey Mouse. Okay? And then wood, it's made of carbon and hydrogen and oxygen, but it's so complex and there's so many different parts to wood, right? Like if you look at wood, it doesn't even all look the same, right? There's dark bits, there's light bits. It's a living organism just like you or I, so it is much more complicated, but it's going to be made of carbon hydrogen, and oxygen, and we don't know how many, so we can just say CXHYOZ, just meaning that we don't know the numbers there. Are you responsible for knowing that? No. Okay, you're not responsible for knowing it, but you should know that wood is not an element. You should know it is something more complicated than an element. It's made of more than one type of atom. And if it is made of more than one type of atom, it is a compound. Water is made of more than one type of element. Therefore, it is a compound. Yeah. And if we look at iron, is iron made of one type of element or more than one type of element? It's made of iron and oxygen, more than one type of element. If it was just iron, that would be an element, but it's iron and oxygen. So it is a compound. But silver, what's silver made of? Just silver atoms. There's no other types of atoms, so that is an element. Okay. Yeah. What is helium? The symbol for helium? He. Is that an element or is that a compound? That is an element. Just helium atoms. Yes. Yeah, for sure. What is the symbol for oxygen? O. Is that a compound or is that an element? That's an element. And plastic, and this is going to be weird, it is C something, H something, O something. Okay? So, in fact, what you'll find is that in the world, there's a very, very, very many things which are made of carbon, hydrogen, and oxygen. Sometimes we'll throw a little nitrogen in there, sometimes we'll throw a little sulfur, but carbon and hydrogen are sort of the basis of almost everything living, and often oxygen is in there as well with a few others. Okay? So is plastic an element? Why not? Tell your partner, why is plastic not an element? So why is plastic not an element? Anyone want to give it a go? Why is plastic not an element? Kyan. It has multiple things in it. There's more than one element. If there's more than one element, it is not an element. It is a compound. Yes, very good. Compound. And potassium is, what's the symbol for potassium? It is K. It's one of those weird ones, right? Probably from the Latin. So that is an element. So who is the odd one out in this series of things here? Plastic. All right. Sand, carbon, bromine, magnesium. Who's the odd one out? Sand. Okay, because you know that carbon is just C, that is an element. Bromine is actually Br2, but because they are both Brs, is there anything different there? No, so it's still an element. And then we have magnesium, which is an element. And so our odd one out is indeed sand. Sand is silicon dioxide. Could you guess the formula for silicon dioxide? Very similar to carbon dioxide. See if you can tell your partner what you think, and then I'll call on you because you had your hand up there, okay? See if you can make a guess as to the formula for silicon dioxide. I promised Mackenzie I'd call on her, sorry. Otherwise, I'd totally love to. Mackenzie, what do you think? I'm gonna come closer so I can hear you. SiCO2? Where did the C come from? SiO2, yes. Is that what you're saying? Yeah, very good. Okay, so we have Si, silicon, and then we have O2. In this unit, you're not responsible for knowing like how many atoms of each type. Okay, that will be for our next unit, but this one, you can just be like, oh, I have two different elements, that is a compound. Silicon dioxide, yes. Now, to be fair, sand can also be many other things other than silicon dioxide. That's just one of the main components. So if you have crushed up shells as a part of your beach, you know, and that's part of your sand, that's probably going to be calcium carbonate, I'm guessing. Okay, so there's different compositions, but that's one of the main ones. Okay. All right. There are many, many different materials in this world, but only around 100 elements, probably around 120 these days. Okay. Precisely 118, very nice. These elements can be combined in many ways to make many thousands and millions of different compounds. If you have an element, how many types of atoms are there in an element? Only one type. And I know it's hard to see on your paper because it's all black and white, but if you look at this sample of copper, all of those atoms are copper. You could be like, this is a Cu, this is a Cu, this is a Cu, Cu. It's only copper, only copper. Carbon, even harder to see the carbon because they're all little black circles, but there's carbon, 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 only carbon atoms. And helium is only helium atoms. So if you have an element, there's only one type of atom. Okay. Now, we're going to introduce another word, and that new word that we are going to introduce is molecule. Okay, molecule. Molecule. Sometimes atoms of some elements join together, and the word that we use in chemistry to say join together is to bond. Okay, so bond means join together. And when those atoms join together, they make molecules. So molecules is more than one atom joined together. What word could I use instead of joined? Bonded. Combined, yes. I'm going to use the word bonded though because that's our chemical science word. Yes? Yeah. So for example, here we have hydrogen. And in nature, hydrogen doesn't float around one little hydrogen atom. Okay, there's hydrogen in the air right now, but it doesn't look like this. It looks like this with the two hydrogen atoms stuck together. Okay? So when we have two hydrogens stuck together, we call that an H2 molecule. Where does that little 2 go? Down at the bottom, right. It's not the protons, that was the bottom left. The top left was the mass number. Now, when we get into writing formulas for chemicals, the little numbers that tell you how many atoms go at the bottom right, okay? So the number of atoms goes at the bottom right. So that's how we write the formula for hydrogen, a hydrogen molecule, and that's what we call it. We call it the formula, H2. And this brings us to a new vocabulary word. The prefix di means two, okay? Di means two. So we can say that a hydrogen molecule is di, which means two, atomic atoms. It is a diatomic molecule. It is a molecule made of two atoms. And it's really common for nonmetals to exist as diatomic molecules. So anytime you have hydrogen floating around in the air, it's always with a little buddy. Okay, it's never just hydrogen, it's always H2. Nitrogen and oxygen and chlorine, they are also all, what's the word? Diatomic, two atoms. So when we write their formula, what's going to go at the bottom right for all of them? a little 2. So if we had chlorine, it would be 2 chlorines stuck together, okay? A molecule is a group of atoms bonded together covalently. We'll start talking about covalently later, so just have heard the word right now, covalent. Don't worry about it. We'll talk about it later. Atoms can also join together to make compounds. So here we were making molecules, but did we make compounds? Is this a compound? H2. Why is this not a compound? Yeah. Doesn't matter if you have 6 of them or 2 of them or whatever, as long it's not a compound because all the atoms are the same. Water molecules are compounds. They're molecules of compounds. H2O. They are molecules. So you can have molecules that are molecules of elements. You can have molecules that are molecules of compounds. It's where you have a nonmetal stuck to another nonmetal. Yes. Okay, those are molecules. Yeah. So we can have atoms joining together to make compounds, and if you remember, a compound is 2 or more different atoms stuck together, bonded. So if we were to take some hydrogen and some oxygen and we were to heat them together, okay, so we applied some heat to it, we would get water vapor, okay? So what we would do is we would take hydrogen, 2 hydrogen molecules. Hydrogen is an element. We combine it with oxygen, which is another element. And now we have different elements in the same molecule, and that's what makes it a compound. And would we like to do this reaction? Would we like to see a demonstration of this reaction? Okay. First of all, we have to make some hydrogen. So let me go grab the stuff and make some hydrogen. Here we have a flask, and into it, we are going to put some zinc. Okay? Now, I'm going to go get some acid, and you're going to see if you can remember from the experiment that we did a little earlier on, what happened when we put acid with zinc. So we have here the acid that you used was 1.0 molar. That was the concentration of hydrochloric acid. Now, you might be able to guess the formula for hydrochloric acid from its name, hydrochloric. What would you guess its formula is? Hydrogen and chlorine. So this is HCl. Okay, so we're going to take some HCl. We're going to put it with some zinc. All right. And then the zinc is actually going to, this is what you'll learn in grade 10. Okay, so this is grade 10 stuff. You'll learn that the zinc can actually take the place of the hydrogen and boot it on out. So instead of having hydrogen with chlorine, the zinc is going to go with the chlorine. Okay, you don't need to write any of this down. Okay, this is totally not what you need this year. So we'll end up with ZnCl2 plus, and then because the hydrogen's been bumped out, we end up with hydrogen on its own. Okay, so that would be our reaction. Hydrochloric acid plus zinc gives us zinc chloride plus hydrogen, and hydrogen is a gas. Okay, so we're going to make some hydrogen gas. I need some way to collect it, so I need a balloon. Okay, now I kind of want this balloon stretched out a little bit. Noises, excellent. Okay, but I want it nice and stretchy so that the gas pressure will let us collect the gas. So I'm just going to pour this hydrochloric acid in here, and I'm going to pop this over the top. And I'm going to swirl it. I'm going to hope this concentration is high enough. I feel like I should have used 6 molar because this is not going very quickly, but we'll see. It may speed up. This particular reaction is one that actually ends up producing some heat as it goes. If you remember, chemical reactions sometimes produce heat. And as it reacts, If this doesn't work, we'll do this again next day and I'll make some of the more concentrated stuff. We just don't have any in the back room. I hadn't thought of doing this today until now, so I wasn't actually prepared for it, although I should have been. Yeah, this is not very exciting. So we're just gonna let it sit and we're gonna see if it does its job. If it doesn't, I'll get the concentrated stuff for next day and we will give it a go with that next day, okay? But we'll see. We'll see if this can manage to produce enough gas to get going, okay? So if you notice the balloon starting to perk up, let me know. There's a little bit of gas in there. There was nothing before, but we'll see. We'll see. Bubbles. Okay. Let us carry on with this while we wait. So this is just our definition of a compound. We've already talked about that. A compound is two or more different elements bonded together. How do you know you have two different elements? In the formula. In the formula, you'll see two capital letters, two or more capital letters. So in the formula, it's very lackluster. I have a feeling we'll be doing this tomorrow. But, oh, hey, hey. Exciting, okay. Okay, so we can have molecules of compounds. So you remember that word covalent? Here you're hearing it again. Again, you don't know about it yet. It's all good. Okay, so we have covalent compounds. They exist as molecules. And molecules are made only of nonmetals. If you have a molecule that has no metals in it, molecules do not contain metals. What's that? Sorry? We would not have a molecule anymore. We would have an ionic crystal lattice, which we'll get to shortly. Okay? Yeah. But they do form compounds, but they form a different type of compound. Okay? So here we have only nonmetals. Where do we find the nonmetals on the periodic table? Over on the right of the staircase. Okay? So they are made exclusively or only from nonmetals, which is to the right of the staircase on the periodic table. So, except for who? Who's not on the right of the staircase but is a nonmetal? Hydrogen. Yeah, do we remember hydrogen? Data pages, let's see. Here are our nonmetals. There's one, just that one, and then all the rest of them are over here. Okay, here's the rest of our nonmetals. Now, when I say exclusively nonmetals, I'm lying a little bit. Metalloids also can form molecules. Okay, so maybe we should add that in to where we were. Okay, so that is over here. 99% of the time you'll be looking at all nonmetals, okay? Only metalloids very, very infrequently. Okay. So here we go. Here we have hydrogen, which is a nonmetal, and oxygen, which is a nonmetal. And we have our formula for water. What is our formula for water? H2O. Where does the 2 go? Bottom right. What does that 2 tell us? That tells us that there are 2 H's. And if I don't put anything, if there's nothing, if there's no number, that means there's how many? Okay, so you have 1 oxygen. Carbon dioxide. It's made of 1 carbon and 2 oxygens. What is the formula for carbon dioxide? Tell your partner, what is the formula for carbon dioxide? Kita, what's the formula? CO2, because you have 1 carbon, so there's no number. So do you remember how I said there's no metals? And you were like, where are the metals? What are the metals doing? Here we come with our metals. Here's an ionic compound. An ionic compound is made of a metal plus a nonmetal. Metal plus a nonmetal. Isn't that a nice name? And they're actually very beautiful crystal lattices. So we have a crystal lattice, and if you're wondering what that looks like in 3D, it looks like this, where you can see there's silver, this silvery colored one, that would represent our sodium, and it alternates with the green one. So it goes, and the green represents the chlorine, because chlorine is usually a greenish kind of a gas. But when you put them together, we have sodium chloride, sodium chloride, sodium chloride, sodium chloride in 3 dimensions. Yes. Yes. Yeah, usually. Yeah. We'll get more into that a little bit later. The question was, how do you know which element to write first? We generally go from left to right in the periodic table. So carbon is to the left of oxygen, so it's CO2. There are exceptions to that, but they're kind of rare, so that's in general how it goes, okay? Also, I will usually either give you the name or the formula, and they will be in the same order. Yeah. Exactly. That one's a little harder to tell, right? Yeah. I keep waiting. Like I think it's a little bigger than it was, but I don't know. We'll see. We got another half an hour for it to go. So, okay. So this is called a crystal lattice, and I cannot draw in 3 dimensions. So very often what we'll do is we'll take a slice of that crystal lattice. It would be as though we took one single layer of this to draw it. and we have alternating sodium ion. So this one here would be, or sorry, this is a chloride ion, Cl minus ion, chloride. And this is our Na plus ion, sodium. Yes. Do you remember what positive and negative charges do to one another? They attract. Where do you notice that the negatives and positives are? Right in between each other. Can you imagine if you tried to put two negatives together? What do two negatives do? They repel. So we never have a positive right beside a positive because those would repel. We never have a negative right beside a negative because those would repel. We just have the positive beside the negative. So it's always positive side negative because they attract. Now, this would be a very, very, very small sodium chloride crystal. There would only be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This would be, if I were to write the actual number of ions in here, I would have Na14, Cl14, and that would be too small for us to even see. Okay, we would not be able to see a crystal that had this many atoms in it. Now, this other one here, we got 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5. Let's just say it's a 6 by 6 by 6. Okay, what's 6 times 6 times 6? 36 times 6 is, I don't know. Where did I put my calculators? 36 times 6 is equal to 216. So this crystal here would be Na 216, Cl 216. But even that would be too small for you to see. And could you ever guarantee that you're going to have two salt crystals the same size? No. So it's not very useful to actually write the actual number of sodiums and chlorides you have. So instead of writing the actual number, we just say that it is a 1-to-1 ratio. Yeah? So we simplify it. We're like, I don't want to write Na216, Cl216. I'm just going to write 1 Na for every 1 Cl. So I just write NaCl. I'm not going to write Na14, Cl14. I'm just going to write NaCl. So we're essentially just using the smallest whole number ratio. It's usually going to be 1-to-1, 1-to-2, maybe 2-to-3 would be like one of the most complicated, okay? So when we write the formula for these ionic compounds, remember they're made of ions, we use the smallest whole number ratio. So we don't have to worry about how big is my crystal, how many atoms are actually in my crystal. We don't have to worry. We know there's 1 sodium for every 1 chloride. Come on, go. Okay. Is this a compound? I have hydrogens and oxygens. No, why not? It's not a compound because, yeah, the two different elements are separate from another. They're not attached. So that's our mixture of hydrogen and oxygen. I feel like I need 6 molar HCl. That's okay. All right. How about this water over here? Is this water a compound? Yes. So yes, compound. So we have one of these that is a compound, one of these that is not a compound. Do I have molecules in this first sample on the left? Do we have molecules in here? Are there molecules? Yes, because we have little atoms that are stuck together, but they're the same, so they're not a compound. So we have molecules, but not compounds. And here we also have molecules. Yes, compound. So one of my favorite questions to ask on a quiz or a test is, are all molecules compounds? Okay, that's going to come up a lot. And the answer is no. Well, let's write down some molecules are compounds, and we'll give a couple examples, and then we'll do some are the other, okay? Are we tired of writing the word molecule? I kind of am. So I'm going to show you an abbreviation for molecule, which is capital M, capital C. Okay, molecule. Some molecules are compounds. For example, H2O, CO2. But other molecules are elements. And for those, can you think of a molecule that is an element? Hydrogen, H2, O2, Cl2. Those are all elements that are molecules. So now we get to the point, why is it safe to put sodium chloride onto fish and chips, but it's not safe to use sodium and chlorine? So sodium chloride, yes. Sodium and chlorine, no. Chlorine is a gas. Chlorine is a toxic gas. It will rip open your lungs and just do nasty things to them. It will react with all the stuff in there. And do you remember what happened when we put the sodium into the water? What happened? Bam! What would happen if you put sodium into your mouth? Bam! Okay, you would have a huge explosion. It would be not nice. So we're not ever going to do that. Okay, we've got this poor man here. Yeah, so you've got sodium also, it doesn't just react with water, it will also react with chlorine. Okay, because what do you remember about the outer shells of atoms? What do they want to be? They want to be stable, they want to be full. So let's imagine that we have a sodium atom. And we're just going to show the outer shell. Is that a stable thing with that one electron there? No, that is unstable. And if we have chlorine, I'm going to draw over top of this little 8 here, chlorine, okay? How many electrons are in the outer shell of chlorine? Can you guess? It's in group 17. 7. 1, 2, 3, 4, 5, 6, 7 electrons. So we have one little hole here, yes? And this is our chlorine atom. It is also unstable. How could these guys make each other happy? Yes. The sodium's going to lose an electron, and the chlorine is going to take it. Okay, so the sodium gives it away, the chlorine takes it. So these two unstable things can make each other stable, and they do so in a very explosive fashion. Okay, when they get together, this reaction releases tons of energy, and what you're left with at the end is you're left with sodium ion and a chloride ion that now has that one extra electron that made its way over. And now both of those are stable, and that is NaCl, sodium chloride. Okay. No, that's going to be a crystal lattice, okay? And yeah, so you'll end up with sodium chloride crystals, salt crystals, basically. Yeah. Okay, so that's why sodium chloride is okay, because all the outer shells are full, so it's nice and stable, but the atoms, the elements on their own are unstable, and that's why you cannot use them. Compounds are very, very much different to the elements from which they are made. compounds are very different to the elements from which they are made. Can you imagine you have carbon? You guys know where you could find some carbon maybe on your desk just right now or close to your desk? The lead of your pencil is actually made of carbon, okay? So this is in pencil lead. Do you know what oxygen does to a fire? It makes it bigger. Oxygen makes the fire bigger. Okay, it makes it hotter, it makes it burn stronger. Okay, it makes the fire bigger. But if you put the carbon together with the oxygen, then you have the stuff that's in the fire extinguisher. So carbon dioxide actually puts fires out. Okay? So oxygen is part of carbon dioxide, but the oxygen on its own makes the fire bigger. The carbon dioxide puts the fire out. So they're completely different. If you combine elements, completely different properties. What's that? I'm not hearing the last couple words. Never mind? Okay. But now that we've repeated it, it's not anymore. Okay, I'm sorry. My poor hearing. Okie dokie. So I'm going to, at this point, let you guys do that. I'm going to see if I can get a little more hydrogen in this by, I'm going to see if I can find a little more concentrated hydrochloric acid. So you guys are going to work on pages 9 through 11? 9 to 11. Oh, yeah. Do pages 9 to 11, and I'm going to go see if I can get us more hydrogen. a piece of string. So I don't know what's happened to our string. This is why it's very sad that we don't have a lab aid anymore. They used to keep track of everything for us. Yeah, if you want to work ahead, you can do pages. Actually, you're doing 9 through 11. If you want to work ahead, you can do page 12. Okay? Please excuse this interruption. Good morning, Ruby Mountain. I'm Sadie. I'm Sean. Today is Indigenous Veterans Day. On this day, we honor those Indigenous people who have served and continue to serve in the Canadian Armed Forces and reflect on the sacrifices made by an estimated 1,200 First Nations, Métis, and Inuit peoples across this land. Indigenous people have It is important to acknowledge that Edith Montour, Tony Brick, and Francis Tagamegabau, and all of the other individuals who have made and continue to make tremendous contributions in war efforts despite systematic racism. Thank you. Okay, now the first thing you're going to notice is that this balloon is somewhat buoyant because it contains what kind of gas? Hydrogen gas. Okay? So we're going to take this balloon and we are going to, if we had a little more time, we might generate more hydrogen, but we'll leave it at this for now. We're going to tape it to this meter stick here. And would someone like to hold this? Volunteer to hold this? Ryan? Okay. Okay, and now I have my fancy meter stick here. It's going to pop, but hydrogen is kind of an explosive gas. In fact, have you guys heard of the Hindenburg blimp? Have you heard of the Hindenburg? Okay, it was a lighter than air blimp, but instead of containing helium, it contained hydrogen. And there was a little accident that happened as it came into New York Harbor one year. All the people back in the 1930s, they were like, oh, look, we're coming into New York. Oh, look, it's the Statue of Liberty. How wonderful. And then there was like a tower, and the electricity from the tower arced over to the blimp and basically, thank you. So that was what happened with the Hindenburg. Blow things out when you get a mask on. And it's actually very, very wet on the inside now. That's not because I spit into the balloon when I'm blowing it up. It's because when we have the oxygen in the air combining with the hydrogen, what do we actually get? Water. Yeah, just finishing on time. You can just, no, that's, oh yeah, that's just leave it there, it's fine. Yeah. You mean the book or? Yeah, okay, let me show you. Yeah, because it's nice to be able to go back to it later. So what you would do is you would go to Teams. Actually, let's stop recording.